Hey students, in this clip we're going to be going over some examples on how to find the extreme values of functions using the graphical approach. Alright, so let's take a look at question number 1. So part A, we have to state where the extremas are at. B, we're going to find the local extrema and classify them, stating their location. Part C, we're going to find the value and location of the absolute extrema. And then part D, we're going to indicate the applicability of the extreme value theorem. Alright, so let's start out with part A. We're going to state where the extremas are located. Okay, so the extremas are made up of the local, maximum, and minimum. And you know that the absolute extremas are part of the local max and min. Okay, the absolute extremas. Alright, so where are the local, max, and min? Alright, so if any y value is the highest or lowest in any interval or neighborhood, then it qualifies as an extrema. So if you look here, if you look at this neighborhood right here, this interval, you notice that this is the lowest point, right? So at this point, that is an extrema. So let's go ahead and write them down. Extrema, extreme values are at where they're located. We're not talking about what their values are, but where they're located. So in this case, the first one is at -3. That is a local extrema. And then the next one is at -1, because in this interval right here, this is a high point, okay? In the interior, extremas are basically the peaks and the valleys in the interior, okay? And then when the endpoint is included and is decreasing or increasing to that point is also an extrema. So in this case, we have a peak right here. So that's also an extrema, -1. Over here, we have a valley or a corner. Looks like a cos for a corner, whatever you want to call it. So that's a low point right here. So at 0, we have an extrema. At this high point right here, this is a peak. You also have an extrema at 1. And then at this low point right here, you have an extrema that's 3. And then at this endpoint right here at 5, you have an extrema because that point is higher than every point around it, so that's also an extrema. Alright, so these are all the extrema, the location of the extreme values that we have in this problem. Alright, B part, we're to find the values and classifications of the local extrema, including their locations. So which of these are maximums and which are minimums? Alright, so the B part, let's start with the local. Local, or another word for local, is relative. Okay, local or relative maxima. Okay, maxima is a plural for maximum. Okay, so what are the local or relative maxima? We're going to talk about what the values are and where they're at. Okay, so the first one, let's start from left to right. The first one, this is the first local maxima right here. This is a local maximum. So we have the value of the first one is the value of y equals 3 at, where is it located at x equals -1. So this point right here is a local extrema, a local maxima. And then where's the next local maxima? This is another local maxima, the next peak we have. So the value of the next one, value of y equals 5. That's the y coordinate. If you trace it here, that's 5. And then it's located at x equals 1, right here, x equals 1. Okay, and then the next one is this high point right here, is an endpoint extrema. So that one has a value of y equals 6, and it's at x equals 5. All right, so there goes your local maxima. All right, now let's focus our attention on the local or relative minima. All right, which are the collection of all the minimums, local minimums. All right, so the local or relative minima are as follows. Local or relative minima start with a value. Let's start from the left. We have a value of -3, value of y equals -3, because this is a low point right here. And where does it happen at? At x equals -3. So that's your first local minima. And then the next one is this, it's kind of like a cusp right here. That's a low point in this neighborhood. It's like a valley. So the value of that local minima is 0. Where is it at? Is at x equals 0. All right. Now the next minima is this value right here. It's a low point, so it has a value of y equals, you trace this point to your y-axis, value of y equals -4 at x equals 3. All right, so there goes the local extrema. All right, so next thing we're going to do is find the absolute max and min. So let's start with the absolute maximum. All right, so we can either use our result here, or we can use the graph to determine what the absolute maximum is. Let's use the results here. So if you take a look at all the local maxima that we have, which is the biggest one? The biggest one is clearly y equals 6. So this is our absolute or global maximum. If you look at the graph, what is the biggest output value? It's clearly 6, right? So it's consistent with our results right here. Remember, your absolute extremas are in the set of your local extremas, okay? So keep that in mind. So for part C, we have an absolute or global maximum. It's only one maximum. The value has a value of y equals 6 at value of 6 at x equals 5. X equals 5. All right, and then the absolute or global min, absolute or global minimum has a value of what? So let's look here. Inspect our local or relative minima. Which one is the lowest one? The smallest one is clearly -4. And if you look at the graph, which one is the lowest point? You see, tracing it to the y-axis, this is the lowest point right here. So this is going to be our absolute or global minimum. So value of y equals -4 at x equals 3. All right, so there you have it. All right, so let's indicate our solutions on the graph, even though we have everything down. So let's see. This point right here, this is a local minimum. This point also is a local min. Arrow there, pointing to where we're talking about. So there's a local min. This point right here is a local min, and it also happens to be our absolute minimum. Is the smallest of all the minima. Okay, and then this point right here is a local max, and then this point right here is a local max. And then this point right here has two names. It is a local max, like the others, and it's also your absolute maximum. Absolute or global maximum. Okay, so there you have it. Another point to note is that looking at the interior points, not at the end points, what do you notice about the derivative at these local maxima? You notice here the derivative is 0. The derivative here is 0. The derivative here is 0. And what about the derivative here? Is non-existent. Okay? So what does that tell you? It tells you that in the interior points, if you have a local max or min, the derivative is either 0 or non-existent. Okay, so f prime is equal to 0 or non-existent at the interior extrema. Alright, so keep that in mind. Let's just put that like this. So f prime equals 0 here. Here f prime is equal to 0. Here f prime is equal to 0. And here f prime does not exist. Okay, so there's a special name for these situations. They are known as the critical points. Alright? Anywhere the derivative is 0 or does not exist in the interval of a function, those points are known as the critical points of the function. Okay, so keep that in mind. All right, let's answer part D. Part D, we're asked to say if the extreme value theorem is applicable to this situation. So let's look at the situation. Is the extreme value theorem applicable here? In order for the extreme value to be applicable, there are two conditions that must be met. All right, so for the extreme value, there has to be condition 1, continuity. And then condition 2, you need a closed interval. All right, you need a closed interval. All right, so if you look at this graph, is it continuous on the entire domain? Absolutely, there are no discontinuities. Is the interval closed from -3 to 5? They are, because we have closed circles there. All right, so since this function is continuous and on a closed interval, we can apply the extreme value term here. So the extreme value theorem applies. Value theorem applies. So what does that tell us? It tells us that we guarantee to have an absolute maximum in this function because it meets the initial situation for the extreme value theorem. All right, so D is a check. Extreme value theorem applies here. All right, let's take a look at question number 2. So looking at this graphical situation, where are our extreme values? Okay, so let's start out by doing the A part by listing where our extreme values are located. So extreme values are at x equals, in this situation, these 2 points would have been local, would have been extreme values if they were included. So so they need to be excluded. So these 2 cannot be local extremas since they're excluded. All right, these endpoints are not included in this function, so they have to be excluded. All right, but this point right here is a high point relative to every point in the neighborhood, so it qualifies to be an extrema. So where does that happen? It happens at x equals 0. All right, so in this case we have only one extreme value. All right, part B, we have to state the local extremas and their classifications. So we're just going to focus our attention on this one extreme value we have right here. This is a peak, all right? So it's going to be a maximum. So in this case, we have a local or relative maximum, because it's only one, maximum, with a value of y equals 3 at x equals 0. Okay? And then how about our absolute max or mean? In this case, we have only one extreme value, which is a local max, so this is going to be our absolute or global maximum. All right, so our absolute or global maximum is going to have a value of y equals 3 at x equals 0. All right, so let's go ahead and label it here. This is our local and an absolute maximum. Okay, and then what do you know about the derivative here? At this point, the derivative does not exist. Okay, the derivative is non-existent here. So in this point, f prime dne does not exist. Okay. All right. How about the applicability of the extreme value theorem? So is this function continuous? Good. It is. So it passes the continuity test. How about is it on a closed interval? The answer is no. It's on an open interval. So the extreme value theorem does not apply here because it doesn't satisfy the initial condition that the function must be in a closed interval. So extreme value theorem does not apply. Extreme value theorem does not apply. Okay? Alright, so that's a fail right there. Okay, now let's move on to the next question. Alright, let's take a look at question number 3. So we're going to start out by stating listing where the extreme values are at, part A. So extreme values at x equals. Now this endpoint right here is included, is a low point relative to every point in its neighborhood, so it qualifies as an extreme value. So you have an extreme value at x equals 0. Now look here, this would have been an extreme value, but it's an open circle, so it's gone. There isn't any extreme value there. Over here also would have been an extreme value, but it's an open circle, so it's not an extreme value. Now let's take a look at this point. You have to be really careful when considering points. Now, is this an extreme value? So the question is this point higher than every point in its neighborhood in this function? In order to deal with the classification or the consideration of points as extreme values or not, what you do is you draw a horizontal line through the points intersecting the function. And ask yourself, is that y value higher than every neighborhood point in the entire domain of the function? So if you take a look at this right here, this point has the same value as this point. But does this point qualify as an extreme value? Absolutely not, because relative to the points around it, it's neither a high point or a low point. So that transfers automatically to this point. Okay, since this point and this point intersect and this is not an extreme value, this point is certainly not an extreme value. Alright, so supposing we had a point, let's say we have a point up here. When you draw a horizontal line, you find out that relative to every point in the graph, it's a high point, so it qualifies as an extreme value. But in this case that we have right here, this point is not higher than every point in its neighborhood, namely the points around this point, so it does not qualify as an extreme value. Alright, so in this case we have just one extreme value at x equals -4. I don't know why I put 0 there, sorry about that. So the extreme value there is at x equals -4. Alright? Okay, now the B part is the classification. So in this case we have a local or relative minimum, since there's only one, local or relative minimum with a value of y equals -2 at x equals -4. Alright? And then part C, where is our absolute or global minimum? We have an absolute or global minimum with a value of y equals -2, same as the local, which was the only one we have, at x equals -4. Alright, so let's go ahead and label it. So this one right here is a local and absolute minimum. Okay? Alright, part D, does the extreme value apply here? It evaluates the conditions of the extreme value in two conditions. First of all, it's not a closed interval, and secondly, it's not a continuous function because you have a removable discontinuity here. So since it's discontinuous and not on a closed interval, we have two violations. So the extreme value theorem does not apply. Okay, the extreme value theorem does not apply here. Does not apply. Okay? So there you have it. So thanks so much for taking the time to watch this presentation. Now feel free to subscribe to my channel by clicking here so you can get updates to other cool calculus clips such as this. Please post a comment to let me know what you think, and do give me a thumbs up or like if you liked it. I really appreciate it. And also feel free to share with your friends. More clips can be found on mathgotserved.com/calculus. Thanks again for watching, and have a wonderful day.